my laptop. All right, so we start with support vector machine, and let's see what we have here in the page. Okay, so whatever we've been dealing with so far, right? Whatever we've been dealing with so far with the lines of linear regression, logistic regression, naive Bayes, KNN, I mean, they are all supervised learning, right? They are all classification, and I mean, for logistic, for instance, you can use it um, for regression problems, all right? And support vector machines is also one of them, one of the classification algorithms that you can actually use, right? You can also use it in regression, but mostly we use it for classification, all right? So we have support vector machine, support vector classifier, then support vector regressor. All right, so you can use it for regression. So if it's a regression problem, then you use support vector regressor. If it's a classification problem, then you use support vector classifier, right? So possibly you might be seeing you first, like if you're using the algorithm, we are going to do that when it comes to the code, but I just want to show you over here. You'll be seeing support vector machine, right? SVM, right? So you import SVM. So depending on the particular problem that you're working on, if it is classification problem, then you use SVC, right? Support vector classifier. If it is let me use this one, SVM. So if it is regression, then you're going to use support vector regressor. All right. So you can use it for classification, and you can also use it for regression. All right. And mostly for supervised machine learning algorithm. All right, for supervised machine learning problem. So that's what we will be doing today. All right. For clustering for this for these two, I'm thinking we schedule a day, then we deal with that, right? And then your final project will be based on this dimension reduction, possibly, right? On this dimension reduction. All right. So we will schedule a day, and then we deal with this, right? Then we deal with this one, and then I'll make available these ones for you, right? We'll get rid of that. I'll make available these ones for you so that if you want it, you can get through it and then get to know the concept in there, right? If you're interested in that, I'll make it available for you. All right, so I'm planning for that so that we schedule a day, because these are related concepts that if we do them together, we will actually get the understanding the more rather than doing them separately, right? So maybe instead of 2 hours, we can extend it to say 3 hours or 3.5, right? Then we deal with these two, right? And then for this one, it will be, you combine all these algorithms, of course, you combine all of them, right, to make the project made. Mainly, you will perform some dimension reductions before, you do the final project, right? So you keep your eye on this one here, right? So we will deal with this thing, we will schedule a day and deal with that. So today, let's deal with support vector machine, all right? Okay, so we have the code here, but before we come to the code, let's just get an idea or a basic understanding of support vector machine. All right, let's get the basic understanding of support vector machine here. All right, so with support vector machine, basically what it does is that it tries to separate groups, right? Group of points or something like that. It tried group of data points, of course. It tried to separate them using linear separation, right? So let me just draw this so that you can get it. So let me insert some lines here. Let me draw this, something like that. Okay. If the network disturbed or you have any question, you can just unmute yourself and speak. All right. Okay. So let's say we have this, right? So I'm I'm going to draw some points over here, right? I'm going to draw some points here. So let me use something like let me first start with black points, right? So let's say we have some points somewhere here, right? Let's say we have some points like that. All these are data points, right? So let's say we have some group of data points here. So let's say we have something like this, right? And then let me pick this one. So let's say we have another group of data points over here. Okay, so let's say we have this, right? So what support vector machine does is that it tries to separate these two, right? Try to draw a line to separate these two. So if you can see this, right, you can think of it as we can draw so many lines to separate this. Maybe one line. Let me get this. Okay, so maybe one line will be here, right? We can use this one to separate it, right? So maybe this is a line that's separated, right? And maybe you can also think of it as maybe this line, right? You can think of it as my pen is disturbing me quite a bit. Okay, let me undo this. You can also think of maybe the line passes somewhere here, right? Something like that. Okay, so all these lines separated, and you can draw several lines, right? You can draw several lines that separate this, right? You can draw several lines that are going to separate this. Guys, give me a minute to let me reset this. I think it's disturbing my pen over here. Okay. I hope this will work. Okay, I think it's better now. Okay, so think of these lines, these different lines separating it, and of course you can be drawing several lines that can separate it, right? You can think of it as having several lines that can actually separate it, right? So there are different lines that we can actually use to separate it. But let's just consider these two. All right, so this is what support vector machine will actually try to do to linearly separate these two groups. All right, and as I said, you can draw several lines that will separate this, and choosing the line that best separates this is what support vector machine is all about, right? It tries to choose the line that best separates these groups. All right, that's what support vector machine actually does. And I mean, the difficulty is that if let's say we have a new point here, right? Let's say we have a new point here. So if we put this point here, right? Let me put it here. So let's say we have this new point here, and now we want to classify this new point, right? Now, if we say that we are choosing, let me name this line one. Oh, let me choose this black. Let me name this line one, and then I will name this line two, right? Now, if we decide to choose line one, it means that this new point will be classified as a blue point, all right? However, if we decide to choose line two, I mean, if we decide to choose line one, right, so then this point will become blue. If we decide to choose line two, then this point will actually become a black point. All right, so choosing the line is critical, and that is what support vector machine actually helps us to actually do. You will not see this physically with your eyes, as the algorithm is doing. But I mean, behind the scene, that is what it's actually doing, right? Trying to find the best line that separates two groups that you want to classify. All right, that's behind the scene. That's what it will actually do. So if we are able to separate it like this without some blue points getting into here, maybe some blue, seeing some blue points somewhere here, or seeing some black points somewhere here, right? If we are able to separate these two without any crossovers like that, then we say that these points are linearly separable, right? They are linearly separable, which means that we can separate them without any any cost, right? We can just um, separate them without any cost. All right. However, it's not all points or all groups that you can get it in this way as smooth as this to just draw or find the best line to separate it. All right. It's not all groups that you can do that. So what support vector machine does to get the best line? I'm sorry, guys. Hello, can you guys hear me?
Yes.
Okay, all right. So what support vector machine does to find the best line is to try and then find a margin, right? So let's say, let me use red here, right? Let me use red here. So if you can see, let me actually let me insert, and then bring this. Okay, so what it will actually do is to find a margin here for say L1, right? So we're doing this for L1, right? And then we do that up to the point where we hit the first blue, right? So now what we are doing over here is this. Let me go to draw so that you see it. Let me use green here. Now it's 9 o'clock. Now you can see we have L1 here, right? We have L1 here. This is the L1 line. This is the L1 line. Now what support vector machine does is to find the margin between this and that, right? This and that. That is, it tries to see the first black point, right? Try to draw a line that will hit the first black point and the line that will hit the first blue point, right? And then see the margin that is between that. I mean, the distance, right? So you can think of the margin as a distance, right? Try to find the distance that is between that. It will do the same thing for the blue, right? Try to see where it will first hit the first black point, right? And then draw it like that. My bunker is not that smooth, but just think of it like that, right? Then it will try and then consider it again. That's the L2. We are doing it for L2, where it will hit the first blue point, right? The first blue point is somewhere here, right? So it will draw another one. Okay, it will draw another one. So now it's going to consider this now. The first black point was somewhere here, right? Something like that, right? So now it will compare these two margins. So let's say this one is margin 1, right? And then this one is margin 2. All right, so now it will see that this margin is bigger than this margin, right? Then it will choose this one, which is having the bigger margin, which is the L1 line, right? So L1 line is actually going to be the line that we are going to use to separate these two groups. All right, so that's what support vector machine will actually do. It will do that for different lines that you cannot actually even imagine that can actually separate this, right? Just imagine that we have several lines that can separate these two groups, right? So it will calculate the margin for all these lines, right? It will calculate the margin for all these lines and then find the line that is having the highest or the greatest margin, all right? And then choose that line as the line that will linearly separate these groups. All right, so that's what support vector machine will do to get the margin. All right, so you can call this L1 line as a plane or as a hyperplane, right? This one is just it's an equation of a line like y equals say a plus bx, right? However, if you have say y equals a plus B1 X1, right? And then say B2, let me push it here a bit. Say B2 X2, right? Then this one becomes equation. This one is an equation of a line. That's what we are using to separate this. However, you can get A plus B, B1 X1 plus B2 X2, right? This becomes a plane. All right, and you can also go beyond that, like y equals a plus b1 x1 plus b2 x2 plus say b3 x3 plus some b4 5 a lot of them, right, plus maybe bn xn, something like that. So this one actually becomes a hyper, right? Becomes a hyper plane. All right, becomes a hyperplane. So normally it's actually going to use a hyperplane to separate it. We are just doing this in two-dimensional space, don't forget, right? But it can go all the way to say 5, 6, 7, 20, 50, all right, 100, 200 dimensional space, which we cannot actually even imagine of visualizing it. All right, and that's the work of support vector machine. It will do this part at the back end that you cannot actually see, right? All you will do is to just import the library, the algorithm, and then just fit it on your data. All right. So this is two groups that are separable that you can actually separate it. You can also have it in this way. You can also have it in this way. Let me try another one here. You can have it in this way. Okay. So we're having some black points over here, right? So I'm going to draw the same thing. I'm going to input the same black points over here. So we're having some black points. All right, something like that. And then we also have some blue points. Okay, so in this case, instead of having it separable like this, where we have the blacks, the blacks here, and then we have the blues here, that we can just draw a line and then separate it. Somehow there might be some crossovers where you see some blue points here, right? Some blue point might crossover. So let me pick black and then put it here. You might see some black points here, right? So there will be some crossovers in here. All right, and then in this case, it's actually difficult. Probably it's not going to be smooth like that, right? Somehow, something like that. You can even merge like this, right? With some blue ones crossing over here. All right, something like that. You can actually merge something like this, which you cannot just draw a line like this and then say that this line separates the two, because there are some blue points here and there are some black points at this side too. All right, so in this case, what support vector machine would do is actually still calculate the margin, right? It will still do the margin. Of course, it can also say that there are several lines that can also separate this, right? So let's say that this is our best line, right? Let's just consider L. Let me name it LN, right? So let's say that this is our best line, all right? Let's just imagine like that. And then what support vector machine will actually do is to draw the margin, right? So draw the margin, right? Draw the margin like that. Okay. Now what it's actually going to do over here, right, is that instead of just separating this and then choosing the best line, right, what it's actually going to do is to also find the distance between this blue, right, this blue point all the way there, and then these black points, right, that are crossing, right? So there are a lot of black points that are crossing. I mean, this one to this main line. So all these black points, right, that are crossing, and all these blue points that are crossing, right, it will find all of them. What it's going to do is that it's going to add what is called penalty, right? It's going to add what is called penalty. So instead of just separating it and then leaving it like that, it will say that, okay, I'm still going to separate it. But each time that a point crossover, right? Each time that a point from blue crosses over to black, right? I'm going to add a penalty. And that penalty is going to be the distance between the blue point and then the best line that we are finding, right? So the distance here, right? That's going to be the penalty. Okay, and each time that a black point also crosses over to the blue side, I'm going to find a penalty to it. All right, so the distance over there is going to be what is called a penalty. Okay, so that's what support vector machine actually will do. And remember that in linear regression and then in logistic regression, we did something called the loss function. Right? And also the root mean square error, right? We did something like that. In this case, what it will actually do is to minimize the margin, right? It will actually find the maximum margin, right? But it will try to minimize the margin. Now, the intuition here is to maximize the margin, right? So that it will actually get as much data point outside here, right? As much data point outside here. So the intuition is that it's actually going to try to maximize this, right? And in doing so, you can also think of it. So let's say we have the margin, right? This is what we refer to. Let me bring the green. This is what we refer to as the margin. All right. So let's say we have the margin here. Let's say we have the margin. All right. So instead of maximizing this margin, right? Instead of maximizing this margin, what it's actually going to do is to minimize 1 over the margin, right? Is minimize this. It's actually going to minimize this. All right, just think of this as let's say we have the margin to be 5. Let me go down a bit. Let's say our margin equals 5, right? Now we can maximize the margin, right, to find as great margin as possible, right? Don't forget that this is not the only line that we're going to find. There's going to be several lines that support the vector machine is going to consider before deciding the margin that is appropriate, right? So let's say the maximum margin that we got is 5, right? So what it tried to do to make the calculation simple is say to find 1 over 5, right? Remember 1 over 5 will give us something like 0.5, right? So if the margin is equal to say, let's take 15, right? If we find 1 over 15, right, we are going to get something like 0.06. All right, so if the margin equals say 25, we can find 1 over 25, right, which is actually going to give us something like 0.04. Now you can see that it's actually decreasing, right, from that, right? It's actually decreasing. Right, so what support vector machine would do to minimize the error is to find the margin. That's not the only thing. What it will actually do, as I said, that it will add penalty, right? So with this 1 over margin, right, it will actually come into conclusion as 1 over margin, right, plus the penalty that it will add, right, plus the penalty that it will add. Okay, so if we have the data point and then it's like this where there was no crossover, right, which means that the penalty is going to be 0, right, then we are going to have only 1 over margin, right? We are going to have only this and we are going to minimize this, right? So if there are no penalty, then it's going to be 0, right? But if there's a penalty, in this case, like some points are crossing over, and the penalty is just the distance between each point and the best line, right? The best linear line or plane that we have over here, right? So the distance, so if the distance is say 5, right, then penalty here, right? Penalty here is going to be 5, so this one is going to be +5. Whatever value here is going to be +5. All right, so that's what's actually support vector machine does. And the popular penalty that people use, I mean, the popular name that people use, so you'll be hearing something like hinge loss, right? Hinge loss. So instead of maybe saying 1 over margin plus penalty, you will just hear hinge loss, right? Just like you'll be hearing root mean square and loss function, right? So if you hear something like that, it's just this thing they are talking about. All right, so this is what support vector machine would do, right? And don't forget, we are doing this in two-dimensional space, and it can go beyond that, right? We cannot actually visualize that, so we limit it to this case. But when support vector machine is doing this, you will not actually see what it's doing. You just get your you just fit the support vector machine algorithm on your data, and you're done. The rest of these things are going to be done at the back end, which you will not actually see how it is doing. You just have to understand the reason behind it and how it is actually doing it. All right, and as I said, there's also a case where you cannot even draw a linear line to separate it. Let's take another example. Let's take another example, and then you can also see that one. Let me draw something like this. Okay, so let's say we have this, right? And then we have some blue points here. So we have some blue points here. Let me use this. Okay, so we have some blue points here. So let's take this one for instance, right? Let's say we have something like this. And then we have some red points here. Let me use this. Now, in this case, it's actually going to be very, very difficult to draw a line, right? You cannot just say that I'm going to draw a line like this. Let me use a different. I'm going to draw a line like this to separate it, right? It will not work, or maybe like this or like that. I mean, whatever line that you draw cannot actually separate these two, right? It doesn't work in this way. So in this case, it's just completely inseparable, right? You cannot separate this. Right, it becomes difficult to separate it. All right. So what support vector machine would do? Let me push this thing a bit up. Okay, what support vector machine would do is to let's say we have the center here, right? Let me bring this. Let's say we have the center here. Okay, let's say we have the center here. So what support vector machine would do is to try, and then let's call this one x1, and then call this one s2, right? So what support vector machine would do is to try to find the distance between each of the points and then the center, right? So this one is more like the radius, right? So these red ones are going to have short distance or small distances, but just consider the blue one here. It's going to have large distances, right? It's going to have large distances. So what support vector machine will actually do is to transform this, right? So instead of just having x and then y, so let's say we have x here, we have 1 here. So this is just two-dimensional space. So I'm going to project this into a three-dimensional space. So let's say this is x1, and then our x2, right? So support vector machine will do this and then find a distance between each of these points and then project it and then find another one which is called the x3, right? Project it. So let's say we have that one here, all right? So let me bring this one here. So the red points which are having small distances, right? Those red points which are having small distances will be somewhere here. Okay, so let's say these are the red points that we have, right? And then the blue points which are having huge distances will actually be the ones on top here, which will go a bit up. So doing this is projecting this from just two-dimensional space to three-dimensional space by just creating a different axis here for us, right? So doing this, right, creating this different variable here for us is what we refer to as kernel. So if you see any kernel, it's just nothing but just the way that support vector machine will project this from one space to another, right? Just from one space to another, and then creating different variables out of the existing ones and then helping you to separate it. Now, if you project it this way, right, then you can actually draw a line, right? We can see that we can draw a line. We can now draw this linear line to separate it, right? Now we can separate it using this linear line. Okay, we can separate the red from the blue. So that's what support vector machine would do. So if it has become something like this, which it cannot separate it straight away with a line like this, right? Just with a linear line like that, then it will project it, right? It will just transform the whole data into a different form where it can help to separate it, right? And doing so, we use what is called the kernel to do that, right? So this is just a hyperparameter in the support vector classifier or the support vector regressor, right? So when you're using it, you'll come across a parameter called kernel, right? And you can manipulate it the way you want, right? You just as per your requirement and how you want to you want your model to fit, you can actually manipulate this kernel. All right, so let's see. I think I put something here. I did, yeah. Now it's the same thing that I use this code to project over here, right? So now you can see this one like this, right? So it will project it into this form, right? It will project it from just this that you can see, just two-dimensional space, to this kind of space where you can actually separate it. Now you can see over here that you can, with this, you cannot actually draw a line like this or either like that or like that to separate it, right? But if it comes to let me undo this right here. If it comes to this space, right, you can actually draw a plane here, right? I didn't want that. Okay, you can draw a plane here, right, to separate the two. So now you have your blue points here, right? You have your blue here. You have your blue points here, and then you have your red points here. Now you can actually see that you've been able to separate it, all right? And I have also a video on this one. So I mean, a visual transformation of this one. So if you're interested, you can also see that one. If you go to say, let me just go to YouTube. Let me use this one. I hope you can see my screen, right?
Yeah.
Okay, all right. So if you go to YouTube and then you go to the TDS channel, you can see a visual representation of this over there. Yeah, you can see this one over here. Okay, now you can see the yellow points coming there, right? Now you can see some of the blue points are also there. Let me maybe make it a bit bigger for you. Right, now it will project and then you can see the red points being separated from the blue points like that. Now we can draw a plane, right? We can draw a plane which will separate it like this. Okay, you can draw a plane which will separate it like that. Okay, so that's basically the intuition behind this, right? That's basically the intuition behind this support vector machine. It tried as much as possible to use linear separation to separate the various groups that.
magnetic moment दिया हुआ है तो पैरामैग्नेटिक है और पैरा है तो कोई भी जान गया कि अभी मैंने बताया था.
Sorry guys. This YouTube messed everything up. Okay, all right, so let's get back. Okay, so let's go to the code and then see how things work. So as I said, with this that we've been working, right, this is for you to get an understanding or get to know how things work at the background. But when you're doing it on the code, you're not actually going to do this. You're not going to do these calculations by hand, right? You're not going to do that by hand, right? Everything will happen at the background without you really knowing what is going on, but there's intuition behind it and you have to understand it that way. All right. Okay, so let's go to the code. Let's go to the code and then see something here. Okay, so over here we are going to classify, as I said, support vector machine. You can use it for regression problem, and then you can also use it for classification problem. All right. So one thing that I did not mention. Let me just go back and then make it clear. Let me go up here. If you hear about that word too, it will not be new to you. All right. So with this one, right, with the first one that we did, we were able to separate it, just draw a line since there was no crossover. Right. We were able to just draw a line to separate it, to just separate the two groups, right? So if we have groups like that, that support vector machine can just separate the groups without giving any penalty or without any crossovers, right? Then we refer to that as hard margin, right? So if you hear any hard margin, then it means that there were no crossovers. The support vector machine was able to just find the margin between the first point that you can find here and the first point that you can find on the other group, and then use that margin to find the best plane or the best line to separate it. All right, so that's what's referred to as the hard margin. We can also, if there was crossovers like this, that it was not straight away able to separate the groups, right? And then you call it soft margin, right? So if you hear soft margin, then that is what people are talking about. So if there are any crossovers like this, then we refer to that as soft margin. All right. So up to this point, is there any question, or we can move to the code? Okay. There's something else I wanted to mention of it has skipped my mind. If I remember, I'll mention it. All right, so let's just get to the code. If I remember it, I'll mention it for you. All right. So over here we are going to actually use letters, right? So letters A from A all the way to Z. All right, we're going to classify letters A to Z. All right, and this is an article that people have been working on, and they created 16,000 different features out of these characters that you can actually use these features to predict a particular letter, right? So if I've put this information here for you, if you want to read about that article, you search for this PW Free and DJ Slate, right? They are the ones who did this kind of data set. Right, so if you see this kind of article, you will get every information that you want to know about this kind of data set that we're going to use here. All right, so it's named as letterdata.csv. All right, so if you want to read a little about that, you can actually see this right? See this article, right? Everything is in there. You can read a little more about that. All right, so we're going to use that. So all these are just manipulated features that they did in order to help to predict particular letter. All right, so if you can see over here, you can see that all these are just randomly distorted letters or features that they use to produce these 20,000 unique stimuli, right? So that we can use to actually make predictions, right? So we have, if you see over here, we have letter here, right? The letter is actually going to be our target, and all these are just the manipulated features that they did to help predict this letter. All right, so we're going to use these features to make that prediction. All right, and over here is the normal libraries that we import, the likes of pandas, numpy, scikit-learn, and then yeah, over here you can see sklearn import SVM. Now you can see we have our support vector machine here. That's what we're going to use for this particular case. And as I keep on mentioning in the previous class, I mean, it's possible you will not use only one algorithm to just make predictions or to build a model, right? You might combine several algorithms to build a model and then choose the one that is best for you. I mean, tune the hyperparameters in several models and then choose the one that is performing best for you. All right. So in this case, for the sake of this tutorial, we are just going to use SVM, right? So support vector machine, we import it from scikit-learn, right? So sklearn over here. All right, and then we load our data sets over here. So as I said, this is going to be our target. The letter here is going to be our target, and the rest of the features here are going to help us predict these letters that we have over here. All right, so normally we use train test split function to split our data. All right, this one we're going to use it manually. We're going to split our data manually. All right, if we check the shape of this data, all right, let me do this. If we check the shape of this data, right, if I do df.shape over here, okay, I have to run this again. Let me even run everything. Let me just run everything, run ourselves. Okay, so it's running. If you can see over here, right? It's black over there, it's running, right? Yeah, now it's done. Now, if we see the shape of it, you can see that we have over 20,000, right? 20,000 rows with 17 different features over here, right? So that's what we're going to use. And instead of using the train test split function, we're just going to do this by hand, right? So if you can see over here, right? np.array, then in df we select all the rows, right? And then we select everything with the exception of this, right? With the exception of the letter. Remember that we have 17 columns, right? So from 1 to 16 is remember it starts from 0, 1, right? So without the 0, so 1, 2, all the way to 16. Right, so that's what we are selecting. And then when we select that, right, let me zoom in a bit. When we select that, we store it in X, right? And then after that, we select only the letter, right? We select only the letter and all the rows in the letter, right? And then we store it in Y. So that's what we're doing over here. And we're doing this manually instead of using the train test split to do that. Right, we can also do that, right? So if you use the train test split, you do all this in one line, right? And you have your X train, you have your S test, Y train, and Y test. You have all of them. You can have all of them on one line, right? So you can just do everything. But in this case, we are doing that manually. So over here, what we're doing is that in X, remember that we've separated X as everything here, right? Everything here. Let me bring my pen and then make it clear to you. All right, so everything here, right? Everything here is something like red. Okay, so everything here all the way to this part, right, is what we are storing in what is called X, right? So this X that you see is this, and then only this one becomes y, right? That's what we are doing over here. Okay, that's what we are having over here. So everything with the exception of the letter is being stored in X, right? Everything with the exception of letter is being stored in X, all right? Then everything, I mean, with the X, I mean, with the letter, we store it in Y. That's what is happening here. This is just doing it manually. You could have used the train test split to do this just once, right? Then over here, we are seeing that everything, right? Or the first 16,000, right? The first 16,000 and all the columns, right? In X, right? We store it in what is called the X string. And then the last 16,000, right? The last 16,000 and all the columns, we store in what is called the X list, right? Remember, we are choosing this from the X. And then we do the same thing for the Y, right? So the first 16,000, we store it in Y train. The last 16,000, we store it in Y test. All right, so this is just a manual way of doing it. You could have used the train test split to do this, all right? So in this case, we are not doing exploratory data analysis where we are actually going to do visualizations and stuff like that. We are moving on straight to do our SVM, all right? So for that, I think with the previous videos that we've been doing or the previous tutorials, I think that part is okay, where you check if there are null values, if there are correlations and stuff like that, right? In this one, we are not doing that, all right? You can also do that if you, I mean, after loading the data, you can also be doing that, okay? In this case, we are not going to do that. We are moving on straight. So now, since we said that this is going to be a classification problem, we are going to use what is called the SVC. Hello? Is someone talking? All right, so we are going to use the SVC, which is the support vector classifier. So in support vector machine, we are going to use the support vector classifier. All right, and these are hyperparameters that you can actually check from the SVC, right? Now, if as I said, if you see any code anywhere, right, that you don't get any of the hyperparameters, just use that one, and then you can read it from the documentation, right? So if I do this and then go here, go to the documentation, right? You can see the various hyperparameters that you can use. C, kernel, right? You remember we talked about kernel, degree, gammas, coefficient or something like that, shrinking, probability, all right? There's a lot of hyperparameters that you can use. And apart from that, there's an explanation of each of these hyperparameters of in how you're going to use it, and then there's an example for that too, right? So don't forget your documentation. It should always be with you. It should always be one of the things that you should be visiting regularly. All right. So as I said, the penalty C is nothing but a penalty. If you don't get anything, I mean any of these, you just, or if you want to manipulate it, for instance, here we did not even bring kernel. You could have added kernel here, right? You could have added, if you don't bring it by default, it becomes RBF, something called the RBF, right? And I mean, you could have manipulated everything that we are doing over here. All right, so I'm going to get that in off. If you get the notebook, you can just manipulate it as much as you want. All right, this is whatever we want to do is to see that if you have a classification problem, you can use any of these, right? You can use any of these here. That's why I grouped them over here for you. All right, and don't forget some of them are regression, and it's good you get to know that we have, for instance, the support vector machine. We have what is called the support vector machine. Let me bring my pen. We have what is called the SVC and then the SVR, right? So if it is a classification problem, you can still use some support vector machine, right? You can use the support vector machine, but you need to know which support vector machine you're going to use. It's either you're going to use SVR or you're going to use SVC, right? So if the problem is a classification problem, right? If it's a classification problem, you use SVC, right? If it's a regression problem, they use SVR, all right? And most of these algorithms are having that as, I mean, the R, the lies of the regression, and then the lines of classification. All right, so you can use one particular algorithm for different problem statements. All right, so this is just initializing it, and then we store it in what is a variable called a CLF, right, which you can change to any variable that you want. All right, so if you want to read more about it, I've given a link here that you can do that, right? And after that, we are going to use that CLF to fit our data, right? Remember, we've created training and testing data here. So we're going to use that to fit over here, right? You're going to use that to fit over here. Now, if we fit over here, right? So now, if we do that, then this algorithm or this model is learning from this S train and then the Y train over here. All right, it's now learning from that. Now, if it learns from that, you can use it to make some predictions and see how well it is doing. All right, you can use it to make some predictions to see how well it is doing. That's what is happening here. So now this becomes our model, right? This is all we want to build, this CLF, right? That's what we want to build. So make it learn from the training and the testing data. I mean, from the training data, and then use the testing data to verify how well it's doing. So after that, we're using the CLF to make some predictions over here. Right, so CLF.predicts, and then making predictions on S-test, which is the data that it has not learned from or it has not seen. Okay, now if we see the Y predictor, you can see that it's predicting some letters here for us, right? It's predicting some letters, and these letters are ranging from A all the way to Z, right? So it's making, don't forget there's a break here. So you cannot see all the letters that it's predicting. Now, in order to get the accuracy, you could have used the previous measure of accuracy that we use, right? In this case, we are writing a function. So in this project, it's just going a different way from the normal way that we do, where we use the train test plate, then we use all the built-in functions to do it. This is more like manual way of doing it, right? This is more like manual way of doing it, just to show you another way that you can also do it without maybe getting claims to the inbuilt functions, right? You can also create your own and then create your own function. So in this case, it's just creating a function, right? Called get accuracy, right? And then it will get the testing set and then the predictions, right? The testing set, just the testing set is nothing but the testing data that we have here and the predictions that we are making over here. Right, we are storing the predictions. So we make the prediction, then we store it in what is called the Y-pred. So it's going to be, so these are arguments that we are giving for this function, right? And then we are going to initialize this correct to 0, right? Starting from 0. And then if it will check, right? It will check from the length of the test set. That's the length of this, the length of our test data that we have, X test. And then if we use Y test also, right? We can also do that. So you're going to check the test. So this is more dynamic, right? So if you change the above here, you can still use the same function down here, right? So it's going to compare the two and then see if the test that we have and the predictions that we are making is the same, right? Then it will keep on counting. It will keep on counting these and then calculate the percentage that it's getting, right? It will calculate the percentage that it's getting here. So if we apply this get accuracy, right? Get accuracy, if we apply it and then give the argument, remember this argument, this test set is nothing. It's just a variable. We could have just used maybe A and then B over here. This is just a name to know what we are going to use, right? So we could have used any variable here, all right? So this, say A, let me undo here, yeah. So now A will represent our test and then B will represent our prediction, right? So all these are just arguments that we are using over here. So I just use test set and then prediction so that I will know, I mean, I will not get confused later on when I'm using it, so familiar to me. So now if I use this get accuracy function that I created, right? If I use it over here, now I know that this first argument is for the test data. And then the last argument that I created is for the prediction data, right? So I use the Y-pred. Remember that I have my Y-pred over here that is storing the predictions that I created, right? So I'm going to get the accuracy, right? So it's going to go through this, going to compare this, right? Going to compare the test that I have, which is the original data, which is the original test, and then the predictions that my model is making, and then compare the two letters and see if they are matching. It will keep on counting, right? Then after after keeping on counting and reaching the end, it will calculate the percentage for me, right? So the total correct that it got divided by the total test set that I have here, multiplied by 100, right? That will give me the percentage. So that is what it's actually going to do, and then give us this output here. So now you can see that we have around 96%, which is incredibly good, right? So if we print, for instance, the Y grade here is nothing but a column stack of the Y test and then the Y print, right? So column stack here is like this. Is doing something like this. Let's say we have, let me just give a simple example of what column stack is doing. So let's say we have A equals, say 1, 2, 3, right? A equals this, and then we have B equals, say 4, 5, 6, something like this. Now, if we apply column stack on this two, right? Say if you apply column underscore stack on this A and then B, right? If you apply column stack on this A and B, then what it's going to do is it's going to put this in a column, going to put this in a column. So the first A is going to be 1, 2, 3. That's what we have over here, right? And then the B, which is 4, 5, 6. So it's going to give us something like this, right? It's going to do something like that. I'm just, this one is just these things that I'm drawing over here. This. So that's what it's actually doing over here. So column stack of Y test and the Y predict. So the predictions are these are the ones that we are predicting. This is the testing data, the original testing data that we are having. So you can see that the original data was N, we predicted N. The original data was V, we predicted V. The original data was I, we predicted I, all the way to the last one, A. That's why we're having higher accuracy like that. So we're able to match. So only a few, around maybe 3 point something percent, right? Maybe 3 point something percent that we made a mistake. But you can see that at a very high accuracy of 96%, we're able to predict these letters right. All right. So over here, I'm going to actually do, let me zoom out a little bit. I'm actually going to do the confusion matrix down here right now. If you can see this confusion matrix here, this is what I'm going to do. So in order to get these labels, right, the labels that you're seeing down here, right, in order to get these labels that you're seeing here, right, in order to get these labels that you're seeing down here, and also these ones that you're seeing here, right, in order to get to them, that's what I'm going to create this thing that I have up here. So let me go up there and then show you. That's what I'm going to do. So if you use this, I see uppercase, right? If you use this thing over here, it's actually going to help you create this 26 letters, right? Starting from A, let me get rid of that. Starting from A all the way to Z, right? Starting from A all the way to Z. That's what this one is actually going to help us. And then if you see PR here, plus, and then the S for S in lab, don't forget this lab is actually going to contain A all the way to Z, right? So let's say lab is equal to this, right? A to Z, right? And then P lab is actually going to be given this PR, PRA, PRB, PRC, I mean small r, PRC, PRD, right? So it's going to do that until it gets to PRZ, right? So that's what P lab is also going to contain, right? So that's what it's going to create over here. And I did that because I wanted this label. So for the lab label, I'll use the label here, right? And then for the PR, I'll use it here. I created this because I want to compare the predicted A, right? The predicted A, and then the original A, right? I want to create a label here so that I'll compare the predicted A, right? Which is this one, right? So if I take, say, predicted A, right, the number of A's I was able to predict correct, then I'll compare it with the original one. Or say, if I pick, say, predicted Z, then I'll kind of compare it with the original Z, and then see the number that I was able to predict right. All right, so that's why I just created this label. Right, so you could have, skip this part of the code, but it's actually going to help you to, this part of the code, but it's actually going to help you to build this confusion matrix intuitively. Okay. So this is where the confusion we start to build the confusion matrix, right? So from sklearn we import matrix, right? We import matrix, which in matrix we are going to use confusion matrix from this matrix, right? So Seaborn is actually going to help us to plot, right? If you see SNS here, dot heat map is actually going to help us to use heat map to plot this heat map, right? If we don't plot the heat map and then we use only the confusion matrix, it's not that visually appealing for us to get interpretation for that. All right, but if you use the heat map, you actually get it. It becomes visually appealing, and if you want to interpret it, it becomes simple and easier to do that. Okay, so we created the confusion matrix on the x test and then the y prediction, right? Remember we did some predictions over here, right? Y pred is over here, right? We did y pred over here. So and then we have our y test over here too. The lab is just the label that we created over here, which contains A to Z, right? That's the label that we have. So the label, I'm saying that the label should be this, right? So that we have it, we will have this label, right? We have this label. And then from here, I'm putting everything in a data frame, right? I'm putting everything in a data frame. So you can see the CM here, which contains the confusion matrix. You can see it over here. And then the index, right? The index should be this. It should index this lab, which is A all the way to Z, right? That's what we created using this axis, here, all right? And then the column should also be the P lab, all right? That's what you have in over here, which is contain the predicted A, predicted B, all the way to predicted Z, all right? That's what you have in over here. So let me just zoom out so that you see it. Okay, so that's what actually you're having here. And then over here is to actually, this is just setting the size. So 20 here, the 20 that you see here is over here. All right, the 20 here is just the length from here all the way to this part is 20. All right, and then if you go up, if we take it up like this, right, so all the way here, right, that's the width. The width should be 16. Right, so that's what we have 16 over here. The width should be 16. And then we are using, in Seaborn, we are using heat map to do this, to do this confusion matrix. So you can see DFCM, this is the confusion, the data frame that we created over here. All right, this is the data frame that we created over here. And then annotate equals true means that we should show these numbers over there. Right, if you take this one off, if I take this one off, then we will not have it, right? We see that everything is turned off, right? Everything is turned off. You cannot see the numbers over there. So annotate is actually, so if you're not getting any of them, just play around it and you get to know what each of these is, or what each of these means. For instance, you can see that I put format here. I put format equals G over here. Now, if you don't actually know what this means, you just delete this and see. Right? Just manipulate it, just delete it, and then run it and see what happens. Then you can actually know what that is actually doing. Now, if we delete that, you can see over here, just look at the diagonals, right? You can see 1, 5, E plus 0, 2. You can see over here, some E plus 0, 2 is that you cannot get the actual values, right? You can get the scientific values over there. If I bring it back, all right, let me bring it back and then run it again. Now you can see that we have the actual values 151, 134, 138, right? So if you don't get any of these, just play around them. You easily get to know what each of them is doing. So let's just see the confusion matrix and then see what it's actually saying. All right, maybe I should reduce the size. Maybe instead of 20, let me see if 18 would do. 18 and then somewhere 15. Let me run it. Okay. I wanted to actually just fit the screen without me scrolling. So let me go 15 to say 12. Okay, a little better. Now, if you can see over here, right? Let me bring my pen. Or maybe go out a little bit up and then zoom in so that you can actually see. Okay, now what this one is actually doing, right? What this one is actually doing. Let me bring my pen here. Now, let's just take, say, K, right? Let's take K and then trace it to the diagonal. And then let's see the predicted K, trace it here. So what this one is actually saying is that, it's actually covering it. Okay, trace it here. And then come to the predicted K and then trace it there. Now, what is this one is actually doing is that out of the 136, I mean, out of the total Ks that we have in our data set, right, we're able to predict 136 Ks as K, right, as K. However, you can see some of the misclassifications, right? You can see some of the misclassifications, right? Two of the Ks, instead of predicting it as K, right, we predicted that K as R, right? So you can see a misclassification here. You can see another one here, right? There's some misclassification here, but you can see majority of the Ks we're able to predict. The same way goes for all the other ones, right? If we take, say, S, for instance, right, and you trace it all the way here, you can see that 157 of the S, right? 157 of the S we're able to predict as S, right? Only a few of them, maybe you can see some one here, and then some one here, right? So only two of them that were wrongly classified. I think there's another one here. So about three of them that were wrongly classified, all right? But majority of them were able to classify them, right? So about 157 of them were able to classify them as S. All right, so our algorithm is actually doing well. If you're building real-time algorithm and it's actually performing 96%, then actually you're doing well, right? And mostly this kind of accuracy happens in the banking sector or in the security sector, high security sector, like the high government security sector, like the FBI, those kind of security sector, and mostly on the health sector. If you're building an algorithm to maybe classify diseases, right, then you need to get this kind of high accuracy. All right, you need to get this kind of high accuracy. Okay, so this is all about support vector machine, right? This classification algorithm. You can also use it for regression algorithm. I mean, regression problem. And mostly you're going to combine this with other algorithms like the ones we've been able to do so far, like the logistic and the naive Bayes and KNN, right? You're going to combine them and then make with a single problem. You're going to combine several algorithms and then build a model on that. All right. So if you have any question, you can ask. Right. If you have any question up to this point, you can ask. You can unmute yourself, or you can just ask in the question. I mean, in the chat box. Is there anything anyone wants to ask? Is there any question? Okay, so since you still have some of the projects pending, we have thinking of a project that we can have where we can combine this support vector machine together with the other algorithms that we have done so far. All right, so that we can have hands-on, right? Especially with manipulating the tuning the hyperparameters over here, right? If you go up a bit, yeah, the gamma, the C, the kernels, and other helper parameters that you can add, right? So if you complete with the ones that we have, right, as I said, we have this one to go, right? And I'm thinking of us getting another session where we can do these two. I mean all these three together, and then finally we can have one major project on this dimension reduction, which of course is going to combine all these, right? Where you apply all these, right, together with what we will do here, all right? So let's try and then finish the project, right? That is pending, right? After I receive these projects, then I will load the support vector machine project also there for you, which you are going to use only support vector machine. Then after that, I'll have a project where you combine these, right? You have projects where you combine this. So possibly tomorrow we can meet. And then if possible, I'll check in the schedule that I have, and if possible, we can meet and then get rid of this K-means, right? And if time permits, we can actually deal with this and then get it on our way, get it out of our way, right? And then we can move on to discuss the project for this, all right? And then after that, with this, let me get rid of that. Okay. After that, with these ones, I'll make them available as at when they make available. I'll just give you access to it. All right. So you can actually get access to these ones anytime that you want. All right. You can get access to these ones. Okay. So if there's any question, I mean, you can ask. If you have any question, you can ask. Recording will be available tomorrow. Remind me to do that. Possibly tomorrow. Yeah. Okay, so let me go ahead and pause this recording. I'll possibly